Hi everyone, in this video I want to go over how we can compose two functions, composition of two functions in general. So hopefully this sounds familiar from previous math courses, but let's say we've got some function f which maps from set A to set B, and then we have a second function g which maps from this same set B into set C. Then we define the composition of g and f as the function that maps from the domain of A into the codomain of G. So it's going to map from A to C. And the way that we are going to define this function is we take some element A from set A, we plug it into F. So first we plug it into F, we figure out what the output is, then we take that output, which should be an element from set B, we plug it into the function g, and we see what comes out of function g. So we oftentimes call f the inside function in this case, and g the outside function. So we start on the inside with f, and then we work our way to the outside. So let's take a look at a couple of examples. So let's let f be a function mapping from the reals into the reals, defined by each element x gets mapped to x squared plus 1. So this we oftentimes write out using function notation as f of x is equal to x squared plus 1. And for the function g, this is taking each element x in the real numbers and mapping it to 3x plus 2 to get output, which is also a real number. So let's figure out what the formulas would be for each of these composite functions below. So in number one, we're composing g with f. So this means f is the inside function, g is the outside function. So we start with f. And so what that composition would look like would be we're going to take f and plug it into function g. So f was x squared plus 1. So we're going to take x squared plus 1. And for each x in g, we're going to replace it with x squared plus 1. So then we would multiply the 3, group our terms. So when we compose g with f, we get 3x squared plus 5. In 2, we're going to switch the order around. So now we're going to first have the inside function g going into the outside function f afterwards. So this means we now take g, which is 3x plus 2, and we are going to plug that in for each x in the expression for f of x. So over here, we put in 3x plus 2, we square it, and then we add 1, and that gives us 9x squared plus 12x plus 5. Next up, in 3, we can compose a function with itself. So here, we're going to take f and then compose it with itself. So this means we're going to take f of x was x squared plus 1, and then we're going to replace each x in f of x with x squared plus 1. So that comes out to x to the 4th plus 2x squared plus 2. And then lastly, if we want to compose g with itself, then we're going to plug 3x plus 2 in for each x in g. So that would give us 3 times 3x plus 2 plus 2. So that gives us 9x plus 8. So hopefully these problems sound familiar. Let's take a look at one more example on the next slide. So let's consider the following example where now we don't have formulas, but we're going to represent our functions as a Cartesian product of sets. So we're going to let A be the set of 3 elements, 2, 4, and 6. B has 1, 3, 5, and 7. C is the set 10, 20, 30. And so I'm going to define function f, which takes elements from A and maps them to an element in set B. And these mappings are given by this set over here. So this means 2 gets mapped to 5, 4 gets mapped to 7, 6 gets mapped to 3. And similarly for G, we're going to map each element in B to one element in C. And these mappings are defined over here. And so before we think about composing these functions, let's first review some properties of functions more generally. In particular, what does it mean for functions to be injective and surjective? So for injective, recall that a function is injective if every input gets its own unique output. So in other words, two distinct inputs in the domain can't get mapped to the same output in the range. So let's take a look at f and see if f satisfies this property. So here's f. Element 2 gets mapped to 5, 4 to 7, and 6 gets mapped to 3. So since 2, 4, and 6 all get mapped to a unique element, then no problems here with f being injective. So f is injective since every distinct input gets a distinct output. If we take a look at G, well, now we've got a problem in G with this notion that here we have two different inputs, 1 and 5, which both get mapped to 20. So G would not be injective. And next, for surjectivity, this means that every element in the codomain must have some element from the domain which is mapped to it. So in other words, the codomain and the range should be equal to each other. Every element in the codomain has some element which is mapped to it. So let's take a look at this property for function f. So here, the codomain of f is 1, 3, 5, and 7. And if this is going to be surjective, then all 4 of these values have to be an output, have to be in the range. But the range of f is 5 and 7 and 3. So we're missing 1. There is no element of a which is mapped to 1. So f, therefore, is not surjective. Okay, and so recall that would mean that f is not a bijective function because bijective functions need to be both injective and surjective. G, on the other hand, this is a surjective function since the codomain here is the set C, which has these 3 elements. And we can see that 20 is in the range, 10 is in the range, 30 is in the range. So therefore, every element in C has something which is mapped to it. So that would mean that G is surjective, but it is not injective. Okay, so neither of these functions, f or g, is a bijection. Okay, so now let's take a look at how we can compose these two functions. So if I want to, in part A, evaluate g of f of 4, this means we take 4, we first plug it into f, and then we're going to take that output and plug it into g. So over here, we would have g of f of 4. So we start on the inside, we plug 4 into f, and we see that we get 7 out. And then we take 7 and we plug that into g, and we see that we get 30 out of that. So here we would say that g of f of 4 is equal to 30. In B, we are going to compose these functions in the opposite order. So we're going to take f of g of 3. So this means we first take 3, and we're going to plug that into g, and then we're going to take that output, and then lastly plug that into f. So let's see what happens when we try and do this. So here we have f of g of 3. So we would start first by thinking, well, what is g of 3? Well, g of 3 gives me 10. Then I would want to take 10 and plug it into f. But here we have a problem since the domain of f is A, and 10 is not an element in A. So this is undefined. And now we see why it's important for the order that we compose these things needs to match up with domains and codomains. So I can't compose f with g because if we first go into g, the outputs are in set C, and then I can't necessarily take this output and plug it into F. So these, the codomain of G, the inside function, and the domain of F, which is the outside function, since they're not equal to each other, this composition does not make sense. In part C, we want to evaluate G of F of 10. So here, this would tell us that we should first take 10 and plug it into F, and then take that result and plug it into G. But here we have a problem in that 10 is not in A. So this function F is not defined if the input is 10. So therefore, this one also is undefined. So we need to be really careful about how we compose functions in order for them to make sense. So we'll take a deeper look at these ideas in class together.